righty, let's take our seats for an on-time departure. Okay, Oliver, please proceed.
Okay, brilliant. Thank you. And firstly, thank you to everyone for a really interesting talk so far. It's been a great workshop, so thanks to all the talks and organisers for everything. So, just to introduce myself, I'm Oliver King, a postdoc at the Planetary Atmospheres Group at the University of Leicester. I'm going to give you a bit of an overview of the kind of issues, problems we've been having with using JWST observations of giant planets in the solar system, and then some of the kind of tools and techniques we've been developing to try and fix these and improve the data products. So for a bit of context, these are the observations we've been using. So it's near-spec and MIRI IFU observations of all 4 giant planets, Jupiter, Saturn, Uranus and Neptune. So we've been analysing these over the last year or so from ERS GTO observations. And I won't bore you with all the kind of science details about these targets, but the kind of key things for this workshop is these are pretty large, bright targets. So you can see the example Saturn dataset on the right-hand side. Saturn completely fills the MIRI field of view there. We had to do 3 tiles just to get that kind of thin sliver down the middle of Saturn's disk. And these are really complex spectra. So you can see the example spectra at the bottom, a kind of spectral range full of features all the way through, and a really big dynamic range. So you've got really dark spectra around this kind of 6 micron region where you're really pushing the limits of what we could detect with the integration times we used, and then parts of the spectrum around 12 microns where we're experiencing saturation as well. So these big dynamic ranges, lots of complex spectral features, which kind of quite interesting, as I'll talk about a bit later. And the other key things about the giant planets, they're really well characterized. We kind of, because of all the various missions that have been there before, the ground-based observations and so on, we kind of knew roughly what we were expecting. JWST was obviously incredible, kind of discovering lots of new exciting things. We knew roughly what we would expect these to look like, which is then quite useful for when we're identifying problems with the data and then trying to fix them. So kind of 3 main issues that I'll talk about today that we've been developing techniques to fix. There's wavelength calibration that I'll talk about first, then desaturation, and then finally a kind of flat field correction. So these are things that all of our group have been working on. I'm going to give you a summary of the different work that everyone's been doing to try and fix these things and improve the data sets. So first off, we've got wavelength calibrations. This is something that Jake Harkett, a PhD student in our group, has been working on, doing lots of incredible work on this. So all the kind of credit to him, and any mistakes are me in the telling of this. So when we first got the data, this was Jupiter observations last summer. We noticed immediately there were kind of significant wavelength offsets in the data. So the graph on the right-hand side is MIRI MRS spectra in red, and then a modelled atmospheric spectrum in black. And this part of the spectrum is really well characterized. We know exactly where these methane absorption features should be in the spectrum, and the observed data, the features weren't what we expected. So we noticed in the spectrum these kind of wavelength calibration offsets, they varied in position on the detector, they varied with wavelength, and it kind of made the images really messy and hard to understand, and then really hard for us to model. And especially with the kind of really sharp absorption features around here, we just couldn't fit these spectra at all. So what Jake did was he developed a routine to fit these calibration offsets. So basically, at each wavelength with each spectrum, at each spaxel, because of the spatial variation, this added a slight shift to the wavelengths of the MIRI data to then match it up with our modelled atmospheric spectra of where we'd expect these wavelength, these features to be. This worked really well and managed to fit the wavelength offsets for every single spaxel, all the channels up to about 15 microns. With lots of background back and forth with the help desk, interaction with them. This has then since been incorporated into the main calibration pipeline. So all MIRI data up to about 15 microns is now calibrated using atmospheric spectra as kind of part of the calibration routine. And the atmospheric spectra are really useful for this because they've got features all the way through this spectral range. So just going back to this slide, all of these features kind of every kind of few nanometers, we've got another absorption feature which we can use to kind of check the calibration and make sure there's no calibration drifts in the wavelengths across this range. This has now been incorporated into the standard pipeline, as I said, so all data sets are now kind of calibrated using these routines that Jake was developing to make sure that the wavelength calibration is good across the whole range. The next major issue that we're dealing with is saturation. So as I was saying, we've got really high dynamic ranges in the spectrum that we're observing. So we want to be able to integrate to get a good signal in the low noise regions, but also some brighter parts of the spectrum, so like these hydrocarbon emissions around 12 microns, we end up with complete saturation. And then for Jupiter, as we've been hearing with kind of persistence issues before, Jupiter's really bright. So even at the shortest possible integration times, you're still getting saturation in some parts of the spectrum. So just on the right-hand side here, the black line is the kind of observed spectrum that comes out of the standard pipeline, and the red dotted line is what we kind of expect to see. So these bright emission features around 12 microns on Saturn for this example. So what we've done is we've developed a desaturation routine, which we can apply to a spectrum to fix this and produce a kind of full desaturated spectrum. So this uses the groups in the data. So as I'm sure you all know, that kind of as you do the integration, you have the successive groups, and the fewer groups have effectively a shorter integration time. So the full 5-group data, so you can see that is the red spectrum on the right-hand side. In quite a few regions, this becomes saturated. You lose the data. It's kind of flagged by the pipeline, leading to these gaps in the spectral coverage. But for example, the 2 or 3 group data is completely unsaturated and is usable in these saturated regions. So what we can do is develop a routine to automatically identify this, flag the regions that are saturated, and then replace those with good data from fewer groups. So the routine, it starts off with the 5-group data, and then if there's saturation, it will then try and replace it with 4-group data, and then successfully with 3 to 1-group data as well. The other thing that we identified is a few regions which have kind of partial saturation, where the pipeline didn't fully identify the saturations, didn't flag these. But by comparing the 5-group data with 4, 3, 2, 1-group data, you can then see that if, as you step down a group, if the brightness increases significantly and it's near kind of saturation threshold, this is probably partially saturated. So we can also fix this as well. And the reason we want to do this rather than just replace the entire cube with a reduced number of groups is because of the high dynamic ranges, that in the bottom of these absorption features, we still want to get the good signal to noise that we get from having more groups, but at the top of these emission features. This is just an example of when we zoom out to look at the whole spectral range of this cube. And you can see that for almost the entire spectral range, we're using the 5 groups. So you can see in the subplot at the bottom, kind of all the way along here and over here, we're using 5 groups to the best signal to noise over the entire spectral range. And it's only at these very isolated bright emission features that are saturated that we then step down to the 4, 3, and 2 group data, and then use that to desaturate the cubes and fill in to produce this desaturated spectrum that then reproduces everything. And then comparing this to our modeling code and everything, this looks exactly like we'd expect the spectra to be, which is kind of a good check to make sure they're good. And then you can see in the image at the bottom left, kind of an example of this desaturation. So this is at around 12 microns looking at Saturn's North Pole. So on the left-hand side, before we apply the desaturation, all of the bright stratospheric emission around the North Pole was completely saturated. We had no data there. And we had quite a lot of partial saturation in the kind of southern part of this image, these kind of black parts, which weren't flagged by the pipeline, but look like, and they're saturated and kind of clearly aren't what Saturn looks like. When we run the desaturation code, we then end up with something which has kind of bright pole and a more smooth variation in brightness across the surface. So we're able to use these to kind of reproduce the data that we expect to see and then reconstruct to significantly increase our coverage. The final thing that we've developed is a routine to look at the kind of flat fielding errors that are present across MIRI MRS data. So these images here, again, of Saturn, are as the data looks when it comes out the pipeline. And all of these features, all these kind of stripes and grid patterns and swirls and the kind of slopes across the images, these are all artificial. These are not what Saturn looks like. Saturn should be a kind of relatively smoothly varying brightness with kind of bands going east to west. So these are definitely detector artifacts that we want to fix to actually then reveal the true variation in Saturn's brightness across the atmosphere. So we refer to these as flat field errors, but it might not necessarily be the flat field that's necessarily causing this. It could be residual artifacts with stray light correction step or potentially other things going on. But our routine that I'm going to talk about in a moment to fix this is pretty agnostic about what the cause is. So we just kind of group it all together and call it flat field for simplicity here. So the first thing is we can clearly identify what is flat field and what's real variation across Saturn by using the dithered observations. So obviously we have 4 dithers here, each of them has a slightly different telescope pointing. The flat field features, they're going to be fixed in detector location. So as you move the telescope, they're going to stay in the same location on the detector. But real features on Saturn, as you move the telescope, they're going to move across the detector. So you can use this fact to disambiguate between the flat field features that we want to remove and clean up, and then the real features on Saturn that we want to keep, obviously, because that's where our science is. So we make the assumption this flat field effect is a linear multiplicative effect. So basically the observed flux that we're getting in the science cubes is the flux coming from Saturn, the kind of interesting thing, multiplied by some flat field. And that's the thing that we want to find out. If we can find out what this flat field is, we can then divide the data by that and then get the kind of interesting science. So to do this, we've created a routine which can automatically generate a synthetic flat field at every single wavelength of every single cube. So at each wavelength, we start off with 4 dithered images. So you can see them at the top here. And each of these images has been navigated. So this means that basically every single spaxel has a latitude and longitude on Saturn's surface that we've calculated for it. Now we make the assumption that Saturn's surface is pretty unchanging. The atmosphere won't really have changed in the time scale between these observations. So therefore, pixels which are observing the same latitude-longitude location on Saturn are going to have the same brightness coming from Saturn. So you can see the white crosses in the 4 images at the top. These pixels all observe the same location on Saturn. Therefore, they should have the same flux, and any difference between them, we're going to account for being caused by the flat field effect. So, for example, if we give dither 1 an arbitrary value of brightness of 1, the dither 2 is about 13% brighter, that pixel in dither 3 is about 3 or 4% brighter, and then in dither 4 is about 7% darker. So these ratios are then the values of the flat field. So we can then use these to iteratively build up a whole synthetic flat for this wavelength. So we start off by seeding the flat field with 1 pixel value, and then step out to all the pixels which are matched with that one, using the ratios from the data itself, and then that gives us iteration 2, then iteration 3, we go from previous pixels, again use the matched pixels, and gradually build up this flat field through this series of iterations to propagate these ratios that we've calculated from the data. So effectively, we're kind of bootstrapping this synthetic flat field from the data itself, and use the fact that these dithers observing the same parts of Saturn, and then therefore using that to clean up the data. So in reality, we run for about 50 iterations to allow it to converge on a stable synthetic flat field. And then once we've got the synthetic flat field image for each wavelength, we just have to divide the data by the flat field, and then that allows us to clean it up. So this example, we can see this kind of, for example, the really bright line across the middle of the images here. That's all a synthetic effect we want to clean up. That's identified really nicely in the synthetic flat here. And then when we divide that, we end up with these really nice images of Saturn's atmosphere. So this banding is real, that we kind of see this in Hubble images as well. You get this really nice warm cloud feature, which then moves around with the dithers. So by applying this flat field correction, we're able to clean up the data really nicely and kind of see the true features of Saturn that were obscured by these detector artifacts. And it works really well across a whole range of wavelengths with the different artifacts and patterns. So you can see kind of these really sharp, blocky features at 5 microns, the kind of grid-like patterns at 27 microns, and the kind of smooth variation out of the longest wavelengths. They're all cleaned up, and really allows us to reveal features of Saturn's atmosphere that were just completely obscured by this flat field artifact at the start. There's kind of 2 caveats for this. It worked really well for Saturn and Jupiter data sets. We found Saturn and Jupiter needed different synthetic flat fields. They looked similar but had different values. So again, this suggests it's probably related to some of the target brightness, maybe some of the stray light correction residual artifacts could be causing these kind of flat field effects, in inverted commas. And also, obviously, because of how we generate the data, we need the target to fill the field of view to allow us to then create these synthetic flat fields on the data itself, kind of bootstrapping this flat field correction. But if you have a target that fills the field of view, it should work and seems to work really nicely, as you can kind of see here. So we bundled up these data cleaning and processing routines into a single custom pipeline, like you've been hearing other people have been doing similar things. Or this kind of automatically runs the standard pipeline, just a single line of code, you download your stage 0 data from MAST, put it in, it runs the standard pipeline, runs your data cleaning, reduction, kind of flat field correction, desaturation, and then generates a series of kind of quick look plots and animations like you can see here. So it's really nice kind of when you get new data, it's downlinked, run this code, and then you kind of see all your quick look plots and reduce data within half an hour. So it's quite exciting when you get new data, kind of dig into it straight away. So all of our code, it's on GitHub. You can see the link here, and we published a research note as well that kind of summarizes some of the data cleaning processes and techniques we've been putting together. But that's all accessible from that GitHub link there. So in summary, we're doing a variety of things with these kind of extreme observations of giant planets. So Jake did a lot of work with wavelength calibration that's now been folded into the standard wavelength calibration for MIRI, and then particularly this desaturation using the groups in the data sets and synthetic flat fielding using the dithers in the data sets really allow us to clean up the data and produce as good a data sets as we can for these giant planet observations. So thank you. Any questions?
Thank you. Very impressive. Very, very impressive. Yeah, I'm busy typing comments, so are other people. So let's see. There's a little bit of discussion about the groups that are maybe partially saturated. We kind of thought the pipeline handled that, but maybe we've seen that in other circumstances. The people typing. What's the story there?
With the partial saturation.
Yeah, is the pipeline actually, it sounds like the pipeline is, because the pipeline, you did this exercise yourself in very great detail to make sure everything's going on, was working. But it sort of sounded like in some cases the pipeline thought a group was unsaturated, but it was really partially saturated?
Yeah, so it wasn't often we saw this, and this was particularly for the Saturn observations, which were kind of last year. So I think the pipeline's improved slightly since then. But there were a few bits where that we didn't really expect to see it, but you can see here, for example, the 5 group data in red is clearly a lower flux than the 4, 3, 2, and 1 group data.
Yeah.
Up here. So it's in almost all the situations, it's identified properly, kind of flagged in the pipeline. There were the odd bits that were partially saturated, which, kind of quite easy once you look at the different numbers of groups to flag them like this, where there's kind of a 10-20% difference in brightness. But it's kind of.
I believe you got it exactly right by doing this exercise. I'm worried about the pipeline getting it right for people that don't look at this. So, all right. If anybody has experienced this in other non-enormously bright solar system objects, if you could just add that experience to the thread here, that would be awesome. Maybe one more question. What percentage correction did you wind up making with your effective flat fields? Was it sort of? Oh no, that was answered 0.9 to 1.1. I saw that it was answered too after I saw your question, but now you've edited.
Yeah, it varied with wavelength, but generally it was kind of within that 10% range. Very rarely got bigger than that.
All right. Well, we'll just stop here. Thank you for an excellent talk.
Thank you.
Up, also online, Francois.
You will need to share your screen. Yes, we see it. Can you say something so we can hear? We cannot hear you.
We're not hearing you.
And now can you hear me?
Now we hear you very well.
Okay. Too much maybe? Like this is better?
Everything's good, right?
Yeah.
Yeah. Well, go ahead.
Okay.
Maybe if you can put it as slide in presentation, perfect. Yeah.
Okay. Okay. So first, I would like to thank the organizer for accepting this contribution. So it's collaborative work between Laboratoire des Signaux et Systèmes, Signal and System Laboratory and Institut Astrophysique Spatiale. So I'm a French researcher. And the work is about wideband image fusion for producing high-resolution images. So it's a very high-level pipeline. So we consider that we want to estimate or reconstruct a sky that is hyperspectral images, that is 2D plus the wavelengths, and wideband images are these images are affected by spatial blurring that depends on the wavelength and spectral integration. So a common approach is to homogenize the images at the longest wavelengths. So the idea is to blur the image. And what we want to do instead is to propose an inverse problem approach to reconstruct the original 2D plus lambda sky from a set of wideband images. And for this, we need to have a direct model. So at first, we must build an instrument model. So we consider the hyperspectral images with 2 spatial dimensions and the wavelengths. And this cube is spatially covered with monochromatic PSF. We obtain them from WebPSF. And after that, the convoluted images are spectrally integrated with the spectral window to produce wideband images. To do the image fusion, we need to introduce a correlation between the wideband images. We do that with a linear mixing model, where we consider that each pixels is a sum of spectral templates that we consider here to be known, and where the weight of the sum are spatially varying. For instance, we use this spectra that come from NMF of Spitzer IRS measure of NGC 7023. And this model allows to reduce the number of unknowns and introduce a correlation between the wideband images. So when we combine these 2 models, we obtain a linear forward model with details in these blocks. And we use this instrument or direct model to use a variational approach to estimate the weight maps. The variational approach minimizes a criterion where we have data fidelity terms. So we want that estimation reproduce the data up to the noise. And we also add constraints on the offset. We add offsets for each wideband images and positivity on the hyperspectral cube. We have here preliminary results. So there is a website with a link here where we can see these preliminary results. So the first one is a fusion of 4 wideband images for NGC 626. Here we have the measure for the 21 micron images, and here we have the proposed reconstruction, where we can see that there is a lot of, or there is more spatial details. Another example here with Carina, where we make the fusion of these wideband images, and again I show the measure and the reconstruction for the 80 micron images. For these 2 images, we use the spectra, and especially for this one, we add 2 template spectra that are monochromatic. So as a conclusion, we propose a pipeline, high-level data processing pipeline based on the inverse problem for the fusion of wideband images to do, we can say, deconvolution. There is a publication in preparation, and there will be Python code available, publicly available for for everybody. Thanks for your attention, and if you have questions, I'll be pleased to answer them.
Yeah, thanks very much. We don't have time to have live questions, but if you have questions or comments, put it in the chat. I will say this sounds like data analysis tool territory. Could be very interesting.
If there is a question, I don't hear them. So
can you hear me? You missed my whole speech. Sorry. I said we don't have time for questions. Live questions, but people can type them.
okay.
I guess you did hear that. Oh, there we go. Yeah, so the people will type any questions or comments, and I was just noting that this sounds like the sort of application that is good for a data analysis tool, and so it'd be interesting to follow it up in that regard. All right.
Okay.
I will remember to turn on my microphone. Yep, so next up is David Grant.
Yeah. Hi, everyone. I'm David Grant. I'm a postdoc at the University of Bristol in the UK. And in my talk, I'm going to focus in on one very specific step, specifically for the MIRI data, and that's the linearity correction, so all the way back to our group level ramps. And I'm going to talk about some of the issues I've seen with it, and then I'm going to present two algorithms that I've come up with to hopefully improve how linear they are. And so, yeah, in general, this is applicable to MIRI imager data. That's what I've mainly been doing my investigations on, but perhaps it's also applicable to other MIRI modes, as well as maybe some of the other data, but I'll let you be the judge of that. Okay, so I've got just one slide of context, which is if you try and fit your linear up the ramp model to data which isn't linear, you're going to get a biased result. And so in general, we need these ramps to be straight lines. And where this can then affect your science products downstream, for example, absolute flux calibration would be incorrect. It's also a function of the spatial position on the detector. If you don't have uniform illumination, it will depend on that. So that can lead to like augmentations in your morphology or spatial information, the PSF. And then from my science research background in time domain, TSO science, it can also change your relative fluxes through time, and that could induce all kinds of effects in the science that you're trying to do later on. And more than that, because the throughput of MIRI is not uniform, then it can also lead to wavelength-dependent effects. So for these reasons, it's really important that we get the ramps as linear as possible, and we do this correction early on. Okay, so the data I'm going to show you comes from a MIRI LRS slitless dataset from a GTO program, PI Nicole Lewis. And so I'm going to use this grid of pixels throughout my talk. So let's just get orientated with what we're seeing here. So we've got columns and rows, and then we've got some background and a central source in the middle. Okay, so it's pretty easy. And then in general, we also know that each pixel is not just one number, it's also a ramp. And so if you take a pixel away from the source where it's dimmer, we've got a ramp like this. And then if you move to on the dispersion axis, we've got a steeper ramp. And then if you look closely, you can already see the issue where in that steeper ramp, it's clearly not linear already. And I'll just note there are 175 groups in this observation, but I'm only showing every 4 just for visual clarity. And I've also chopped off the first 10 and the final one based on other MIRI effects we already know about, like last frame effect and reset switch charge decay. So I'm just showing the sort of central region. Okay, and then if you fit a straight line to the first, say, 50 groups, you can see that clearly there's like a discrepancy later on. And this is the classical nonlinearity effect that we're expecting, and this is what the pipeline is trying to correct for already. And then if we subtract that linear model from the data, we can then take a look at the residuals. And you can see the residuals increase, and they increase increasingly as you get to higher group numbers and higher fluxes. And then also, so that the algorithms I present to you are somewhat quantitative and we can score them, I'm going to also define a score right now, which is I'm going to take some measure of the variance of your residuals when you subtract a linear ramp from your fit. And in that way, we can quantify whether the algorithms I show you are doing actually any better. So this is, if you took the standard deviation of this residual, that would be the score for this pixel. And if I do it for all the pixels on that left-hand side, you can make a histogram. And so this is what you get if you don't provide any linearity correction. You can see you've got quite a few pixels which actually have small standard deviations, and that's just an artifact of the fact that most of the pixels don't have that much flux on them. And then there's this long tail out to larger values. And so a better, or any linearity correction is hoping to move this distribution towards the left-hand side of the graph. And then just so we're all on the same page to bring it, if you haven't been thinking about linearity recently, I'm just going to quickly describe to you how this effect comes about. And so for Miri, we've got a front contact and a berry contact, and this is one pixel looking in from the side. And then there's a voltage difference between those two. And then inside there, that voltage difference creates a depletion region where all the free charge carriers have been diffused away. And so any photons landing in that region will efficiently migrate to that front contact, change the voltage, and then we'll measure the data numbers. Okay, so a photon comes in, excites an electron into that conduction band, and because of the voltage, the bias, there's an electric field, and that propagates down towards the front contact. You do this with enough electrons, you change the voltage, and then we measure the data numbers. But then about, say, a couple 100,000 electrons later, you can change the voltage significantly such that the size of that depletion region has now been changed as well. And so in this way, you can see how now if a photon lands in that top region, it's not going to efficiently propagate down to the front contact, and it may just recombine at some point. And in that way, we've essentially changed the sensitivity of that pixel, and this is the nonlinearity effect. And so just going back to this picture now, with that in your mind, you can see that as you get to higher group numbers or larger amounts of charge accumulated, the depletion region shrinks and you just lose sensitivity, which is why you get this classic curving down as you get to the end of the ramps. So how does the pipeline currently correct for this? Well, if you measure for a bunch of calibration files and then plot these ramps now as a function of the data number in a ramp versus the data number you would expect for a linear ramp, you can get data which looks something like this. And then you can fit a polynomial to that where the zeroth and first order terms have been held at 0 and 1 because you're expecting some perturbation from a straight line. And then all you have to do is find the optimal, what I've called there, gamma 2, gamma 3, and gamma 4. And this is what the pipeline does. And then you can apply that to the data on the left-hand side again, and you move that distribution towards the left. So the pipeline is doing a nice job, but the question is, could it do slightly better? So I investigated, again, with this grid of pixels on the left-hand side, and if you look closely at the residuals, you can see some quite interesting effects. So we just go through these different subsets one by one. When you're on the dispersion axis, so this is in the brightest region of the detector, you produce these residuals with the white curves. So here you can see that there's excess linearity still left in the ramps, but then just one row over, 1 pixel off the dispersion axis in the pink, you've actually taken away too much linearity. And then once you're in the background region, things look quite nice again. And so currently the correction is essentially a nice average and does a great job. But depending on not just the charge in your current pixel, but also on the adjacent pixels, you actually end up with over or under correcting this linearity effect. So this tells us that there's something else going on. So then returning to this picture of the pixel, they don't exist in isolation. There's pixels either side. And so this is a quick schematic way of describing this effect. But if we have some PSF distribution of the expected data numbers, the central one has been debiased the most and the outer pixels less. And then now if a photon comes in towards the edge of that central pixel, creates an electron, then you've got a small chance, depending on these electric fields relative to each other of the pixels, that electron will be detected in the adjacent pixel. And so relative to what you should have seen, you'll see something like this. And this is known as the brighter fatter effect. And there's a really nice paper from the Miri team describing this. So I would definitely go ahead and read that if you're interested in this effect. And in fact, in that paper, they come up with an electrostatic model which can qualitatively reproduce this effect. So we definitely know what's going on. And now the question is, how can we go about correcting it? So currently, just to remind you, there's some polynomial where if you give it a data number, it will tell you what your data number should have been if you correct for that nonlinear behavior. And so the first algorithm I'm going to present to you is a really simple idea, is to simply segment your data based on the brightness of the pixel, and then do some kind of self-calibrated linearity correction where you can use a small fraction of your data to train those gammas of the polynomial, and then apply that to the rest of your data set. And so for Miri LRS, which I'm showing you here, it's like you can very coarsely essentially just do that column-wise. So for the central column, you could come up with a polynomial, and then you can do the same for the adjacent column. And then at some point, you can just use the same polynomial for the background. And then, so applying this to the same data, this custom correction does an even better job, and it moves all those values even further to the left-hand side. And then, so this correction is actually, I've made it into a custom step in the pipeline. And here's some, like, the most minimal kind of stage 1 code you could write for this reduction. And if you want to add this in, all you have to do is run the custom linearity model and then override the current linearity config file when you actually call your linearity step. And that's how it works. And if you're interested in seeing a science application of this, then you can check out this paper there, and there's a link to the code. It's all open source on GitHub, etc. But there's a few caveats to this first algorithm. One, it's not actually clear how you should segment your data by brightness. Like, how many groups should you have? Where should you cut them off? You're introducing extra gammas, or these coefficients, every time you make an extra group. So you're kind of adding lots of extra parameters. And for data with not that many groups, can you really self-calibrate the data when you've got, say, like 5 groups? So the second algorithm I'm going to present to you is more based on the knowledge that we actually understand kind of what the effects are, the brighter, fatter effect. So maybe we can just correct for that. And this second algorithm relies on sort of these 2 postulates. One is that the classical nonlinearity effect only depends on essentially the bias in your current pixel, and that the brighter, fatter effect only depends on the relative counts between the pixel and the adjacent pixels. And so if those 2 are true, then this correction works very nicely. So if we return one more time to the same grid of pixels, and we just take a group here of 9, so what we're going to do is focus on the central pixel of this 9, and how would the charge be migrating or spread around based on the relative brightness of its neighbors. So based on what I've said, what will happen is that the pixels that are sharing sides with that central pixel will share charge more easily than the corners, because there's a larger overlap. And then on top of that, the second effect is the relative fluxes in each of those pixels. So if you just look at the row of that 9, the charge nicely wants to spill over towards the dimmer pixels. But then in the column, even though it's also sharing its sides, the fluxes are pretty similar, so there's not much charge sharing. And then again for the corners, that if given the same difference, you'd expect a smaller amount of charge to propagate because they're only sharing corners. And so from this, you can easily just write, oh, sorry, one second. Okay, so then just again for a different subset now on the dispersion axis is the same thing again, but this time all the charge would propagate outwards. Okay, so then all I've written down now is a very simple matrix which says the alphas tell you how well can charge move between pixels which share sides, and the betas tell you how well can charge move between pixels which only share corners. And then all you have to do is then multiply that by the difference between the counts of those adjacent pixels, and that can tell you somehow how much charge to put back to where it came from. And then, okay, here's an equation, but I'll just talk you through it very quickly. What I'm saying is that the data numbers you should have received in that central pixel are the data number of the central pixel plus this perturbation, which is the difference between that pixel and an adjacent pixel multiplied by either an alpha or beta, depending on if you're on the corner or you share a side. And then you can just learn those alpha and betas by taking any data that you have in hand and optimizing them such that you linearize the slopes with like any kind of loss function you want, but I just use L2 loss. And then with those new data numbers, you can just put them into the pipelines default linearity correction step, which has this nice fact that if the gammas were derived in that step based on, say, flat fields, then you're actually controlling for the brighter fatter effect already in that correction step because the fluence is even across the detector. And so in this way, the first equation puts back the charge to the pixels it was generated in, and the second equation then accounts for the classical effect. And there are a few nice sort of artifacts of this algorithm. Firstly, that first equation is actually data number conserving because you're only adding and subtracting them equally between which pixel you're in. There are a few free parameters in this formalism, only the alpha and beta you need to find out. And I've actually tested this on 3 different data sets, and I found the alpha and beta came out the same in each case. So there's even the possibility that the alpha and beta are just characteristic to the MIRI detector, and so you don't even need to do self-calibration, you can just set them. Yeah, and I said that the gammas can just come from, say, flat field controlled calibrations. And so applying this algorithm to the same data set, it does even better again. It shifts the histogram really far over to the left-hand side. Okay, and then I'm just going to briefly mention these 2 effects that additionally they complicate the picture even more. One, that there's this odd even row effect in MIRI, which means that your differences may be offset from row to row, so that potentially complicates the procedure. And additionally, I've seen, and lots of people have seen this evidence of charge trapping in MIRI, so in the time series observations area, there may also be a time dependence to some of these effects. And so I don't know the answers to how to incorporate these yet, but just to put them there, food for thought. Okay, and then just to sum up, to show all of these corrections together, here you're seeing the distributions for no correction and then the default pipeline correction for those same pixels I've been showing throughout. And then if you do the first algorithm where you segment the data, you do slightly better. And then if you apply the final algorithm I just showed you, you can do even better again. And so the score on the left-hand side is just the mean of each of those distributions. And so you can see it's quite effective. So in summary, if you want to linearize your ramps and you are worried about the brighter fatter effect, then you could first try segmenting your data into different pixel brightnesses. Or perhaps better still, you can try and actually put the charge back into the pixel it came from, applying this second algorithm I showed you. And then as a final thought, as this algorithm is trying to correct for the brighter fatter effect, I was thinking of calling it the dimmer slimmer algorithm. And I'll leave it there. Thanks.
Awesome. You'll see in the comments that people were like anticipating where you were going, and like, oh yeah, there we go. We'll have one live comment here, and then we'll go online. Excuse me, please.
Okay, I'm Drake Deming from the University of Maryland, and my question is, so the brighter fatter depends on contrast between adjacent pixels, and most of that contrast is spatial, because the star spectrum doesn't change very rapidly with wavelength, and you don't really care, and when you're taking spectra, you don't really care about the spatial dimension. You can add all those up, so why not just add them all, and instead of putting the charge back, just add it all up?
Well, I guess the question, probably the fundamental point there is that, is the charge actually conserved when you spread it out on the detector? And I guess the question is, if you spread it out and you create nonlinear ramps, and then you fit the ramps with a linear model, you're going to be biased in some way in different directions in the central pixel and then 1 pixel out. So the question is, does the 2 effects cancel out and then create an accurate number? And I guess the question, probably the answer is probably it doesn't, although the effect may be small. Yeah.
All right, we'll try to sneak one more in. Everett is typing a super long comment, it hasn't come out yet, so we'll have to do that offline.
Okay.
Let's see, maybe we'll go with what values of alpha and beta have you found? There's maybe a component from IPC, and so maybe you comment on that as we switch to the next person.
Yeah, the values of alpha and beta I was getting out were, for alpha was about 0.15, so about 15% of the difference. and for beta about 0.03, so 3%. So intuitively, they make sense that you share more when you're sharing a side, and you share less when you're just sharing a corner. But I can't speak to whether those are, like, if you take an electrostatic model, you could probably also model an alpha and beta and see how they match up. For IPC, I'm not so sure.
Thank you. Anna, if you want to start sharing your screen.
Yes. Yeah, this is okay.
Thank you.
I hear you, and the screen looks good, so go.
All right, thank you. Yeah, so I'm Anna de Graaf. I'm sorry I can't be there in person. We actually had a big outreach event here yesterday in the Netherlands to celebrate 1 year of James Webb. But I'm glad I can combine the two this week by being here virtually. So I'll talk a little bit about work I've been doing or leading within the NERSPEC GTO team. And now also I'm applying this within some geo programs. And that is based on forward modeling NERSPEC. And I have, I think, a few solutions to offer, but also will highlight a few problems that we still have and are struggling with. So we've talked a lot about IFU in the last few talks. So I kind of want to switch gears and go to the MOS mode and remind you of the fact that there are a lot of moving parts within NERSPEC. And this is great. So you can open and close as you wish, or at least most of them you can open and close as you wish. And it allows you to really flexibly do spectroscopy. So actually my favorite commissioning image is still this one, because it's actually really amazing that this is working. So it's a very popular mode. So I looked up the statistics within cycle 2, 12% of all observing time is going to the MOS mode. As part of the GTO team, I think we've accumulated or are accumulating about 900 hours of data just with this mode. So by the end of cycle 2, we'll have at least 15,000, if not more, extragalactic targets that have been observed with the MSA. And actually, most of these are observed in multiple dispersers. So that is the PRISM, is very popular, and then in combination with a higher resolution grading to really enable a whole lot of science. And although this is a really great tool to have, there are also quite a lot of issues that were noted already pretty early on. And I think the biggest issue that was kind of identified is that these shutters are very small. And how you place them on a source really affects what you get out. So this is kind of a nice figure that Michael Maceda made, showing if you have a source and you put your microshutter on it, you don't always have full control of where it falls. So actually you get a very different part of your galaxy and a very different flux through your slit, depending on where exactly the telescope is pointing. So this is the slit loss problem, and this is partially geometrical, it's partially absolute flux calibration issues, and this is one of the key issues I'll talk about. I just want to highlight some of the other issues though that we have. So there are the slit losses that are kind of relative calibration issues. The absolute calibration is also something that I think there's been a lot of progress, but there's still improvements to be made there. And then I'll talk about kind of the wavelength calibration that we've looked at, and in particular, the instrumental broadening. So that's the line spread function essentially of the instrument. So what are the issues, or why is it so hard to do this? And it has come up in many talks now. So the undersampling, there's some echo. So the undersampling of the PSF is really a major issue. And then with the MSA, you also have the extra geometry of just the little microshutters. So here you see an example if you have an extragalactic source that is neither a point source nor something that really fills your slit. And then on the detector, it actually looks something like this. So it's very blocky, and you can actually see the imprints of the bar shadows right there, but it's actually quite tricky to model. They're not perfect shadows because the bars are smaller than the pixel. The second challenge is the PSF. So the PSF for the MOS mode is partially spatial and partially spectral. And it varies extremely rapidly, not just as a function of wavelength, but also as a function of the intra-shutter position. So that's what you're seeing here. So the top is just a linear and the bottom is a log scale. And if you put the source in the center of your shutter, you get something that's perfectly symmetrical. But if you put it in the top, in the corner of your shutter, which is only one detector pixel different, you get a very, very different shape. So these PSF models are essentially images of point sources with infinitely narrow lines. And is something that we developed within the GTO team. Actually, Pierre Ferry, the former PI, developed this software. And so it's not something that's actually publicly available, or well, I've now made it publicly available. But this is not something that is in WebPSF, so to say. So what I've done is to kind of try to combat some of these issues. And I've developed a forward modeling software for the MOS data. And I developed this kind of selfishly for my own science, and that is because I want to do kinematics with the NeurSpec MOS mode, so really exploit kind of the spatial and spectral information that's in these spectra. But actually, there's a whole lot of other stuff that can be done with this software that is useful to many more people than just me. So at its simplest, you can compute path losses, but also look at line spread functions and then do more science analysis as well, that is fitting actual emission lines. And this is on GitHub. There is a paper as well kind of describing the basics. So what does this do? So first of all, this code will let you build a model that is completely noise-free and also doesn't have any PSF in it. And this model can be only a morphology, so just a light profile. And you can also give it a velocity field if you want to. That's what this is showing. And from this model, you construct a model cube. And if you project this cube along one axis, you get kind of the top right. And then we do a PSF convolution. And the PSF convolution is not a simple smoothing with a Gaussian, because as I showed you, the PSF varies extremely rapidly within the shutter. So what we do is we treat a galaxy as kind of a collection of point sources, and then we propagate each of these point sources through to the detector plane. So that's what you see. Here is the PSF convolution. It also includes this bar shadow effect. And finally, then with a trace model, we actually place it on a mock detector, actually on the exact same kind of pixel as your real data would be. It's on the mock detector. And there's also a small convolution with an IPC kernel in there to really try and mimic all the detector effects that are in there. So this is kind of an ideal scenario where your source is perfectly well aligned. Here you see the effects of if your source is not so well aligned and what it does to your observed object. And this is for the same intrinsic galaxy, right? You're just giving it a little offset and rotation. So that's really showing how important it is to do this sort of modeling. Now, for the slit losses then, what you can do is something slightly simpler. So you simply construct a model that has only a light profile. And then you create this model at sparse wavelength bins, essentially. So you can zoom in on one of these and you see, okay, if I put my source profile at a realistic position in my shutter, then the light on my detector will look something like this. And then the code will tell you how much flux actually went through the instrument. And therefore, it will tell you for this wavelength what the slit loss correction should be. And you do this for multiple wavelength steps, and you can simply interpolate kind of to see what is my slit loss correction. Now, this is for a single kind of exposure. But you can imagine that if you open 3 shutters, and you often do kind of a 3-point nodding, then you can derive a correction for each of your nods, and then correct the individual exposures before or after collating. And a very common question that I get asked is, but what if my complex source is not actually a single Sursic profile? And yes, most objects are not. So actually what you can do is you can fit as many surface profiles as you want, or Gaussians, or whatever shapes you prefer, and feed this into the code as simply a list of parameters. This is still not the same as doing a full non-parametric model. That would actually require quite a bit of extra development. But I think there is quite a bit of flexibility in there already to handle quite complex morphologies. And this really kind of circumvents the pipeline steps that really force you to choose a point source or a uniform illuminated slit. This really does something that's in between and really custom for your own object. So you can think about whether you want to do this in the middle of the pipeline run or at the end. Either can be done. Apart from slit losses, we get more. We also can extract the emission lines. As I said, these models are essentially for infinitely narrow emission lines. So that gives you really just the spectral broadening, the instrumental broadening together with the effect of undersampling. And that means you can construct an LSF model for your custom morphology. And this is really crucial because the spectral resolution of NeurSpec depends very strongly on the actual morphology of your source. So for a uniform illumination, the resolution is much lower than for a point source. And I'm just highlighting this figure here because on the JDocs, currently some resolution or dispersion curve is advertised. That is not actually, it's not actually a measurement. It's not even a ground-based measurement, actually. It's just a prediction based on the requirements for NeurSpec. So I think there's a lot of work still to be done on the calibration of this. From the models that we have, we see that a point source is actually almost a factor 2 higher resolution than what is currently sort of being advertised. And it makes a huge difference for any scientific analysis that you might want to do, right? And also for a signal to noise of emission lines, for instance, you get better signal to noise because they're actually narrower lines, so the flux doesn't get spread over more pixels. Just to highlight some science results, so with this forward modeling, I really believe that this is the future in terms of interpreting NeurSpec data to really deal with the undersampling issues. So what I did in my paper is I had high resolution data, and you can see that there is this sort of lossy gradient visible in the 2D combined frame. But then we fit to all the individual exposures simultaneously. So to leverage the signal noise everywhere, but also to really account for the full effect of undersampling everywhere. And with that, we can constrain really the dynamics of galaxies, that are very high redshift. So it's really a completely new thing. I think I'm slowly getting to the end of what I wanted to show you. I just want to share kind of the outstanding issues that are there in my mind. So the slit losses are, in some sense, easy. There are calibration programs ongoing to observe standard stars, and I think we can compare this with things like my code, so that you can combine the calibrations with a software or a piece of software that will then handle your more complex data or predict more complex data. There are still some issues with the absolute calibrations. So at least within the GTO data, we see there's 10% offset between the medium resolution gratings and the prism. And hopefully these calibration programs coming in cycle 2 will help alleviate this. I think a bigger issue is with the wavelength calibration, where both in terms of the LSF, but also just the absolute calibration, there's still major uncertainties in that we don't actually, no one has tried to measure the line spread function, including myself. It's something I'm working on. And it's really hard to do this because of this undersampling. So you really need the right sources, and that's extremely tricky. But also in the wavelength solution, we find pretty big offsets between dispersers. So if we observe the same source with the exact same shutter mask, and back to back, and analyze the data, then we find a systematic offset between, say, the medium resolution grading and the prism that is of the order of 1 detector pixel. So that's 1 detector pixel in the prism data, and that's roughly 10 pixels or so, or 5 pixels in the medium resolution data. So it's really large, and that means that if you want to model the data simultaneously, That's currently simply not possible. And it's, especially if we think about all the sort of black hole science that's currently very popular, it's really important to have this wavelength calibration sorted. And right now there is simply no data for that there yet, and I hope that will come in the future. Okay, so in summary, the MSA is a very popular mode. It's my favorite mode for sure. And I've developed a tool to kind of combat some of the issues that people have encountered in the first year. It can also be used actually to test pipelines. And I hope that with more calibration data, we'll tackle more of the challenges that are there. Thanks.
Alrighty. So we have a couple questions. The first is mine. Sorry, I probably just missed it, but what stage of the pipeline output are you modeling? And then looking at the repository, it seems like you don't use the pipeline software at all in your modeling, right? It's totally independent. So if you could just address those two.
Yeah, so it's totally independent from the ST pipeline. So what you can do, so essentially what I model is a raw detector frame.
Right. Okay.
So it's a very, so I think it's the start of the stage 2 pipeline, if I'm saying it correctly.
So there's so if I could just jump in, there's uncal and then there's rate.
So it would be it's the step just before you make the cutouts.
Okay, I'm guessing rate. Okay, good. And then could you provide some more details about what kinds of dedicated calibrations you'd like to see for the MSA mode rather than scaling from the fixed slit?
Yeah, so there are two things. So for the fixed slit, you don't get the distortion across the detector. And the fixed slit cannot test the wavelength calibration issues that we see, right? You really need to get data across the full MSA to figure out what's going on there. And then for the line spread function, what you need is a source that is a point source. And you need this source to have many features. So that can be either emission line features or absorption line features. And what has been observed so far is a single planetary nebula, which I think we can get a long way with that, but it's not a true point source. And it also, there are not that many emission lines in there. So with the undersampling, it's actually quite hard to then extract a good LSF model. So yeah, my idea would be to use stars. For instance, red giants that have many absorption line features and are bright in the near infrared. And that could also fill your MSA quite nicely.
Okay, perfect. Thank you. If you could put those answers in there and answer the other question that's there for now and any others that come up, that'd be great. Thank you very much.
Thanks.
We are going to switch to some 5-minute talks, 3 of them, and then off to lunch soon.
My name is Driyama, and I'm a postdoc at UMass. And today I'm going to present some of the work we did with the calibration, flux calibration of the NIRCam. So the NIRCam, initial design of the NIRCam, the flux calibration kind of level of error is about like 5%. And this work that we actually want to push that limit to like a sub 2% kind of level. The reason we want to do this is that, just a little bit of context, we have these pearls observations that there are 2 fields that targets the that we want to do the time domain science. So we have 2 blank field. One is called TDF. There's an IDF field. We took multiple epochs of the data with the NIRCam in multiple Bob and filters, and So when we examine this particular data set, IDF, where we have 3 epochs, when we do the subtraction between the 2 epochs, the first 2 epochs, we found that everything becomes a variable because of this mismatch between the module A and the module B flux calibration. So the reason why it's showing up like this is because there, I don't think I have a pointer, but what's showing there is that the observations are designed such that between epoch 1 and epoch 2, the position angle is flipped by 180 degree. So what's the same patch of sky was used to measure in module A in epoch 1 is detected or is observed by module B in epoch 2 and vice versa. So it's more complex for the short wavelength modules because in the short wavelength modules we have 4 subarray or 4 chips. So each of them, because the labeling of those subarrays is center symmetric, so when we flip, so what's in array A1 in epoch 1, then you become array B1 in epoch 2. So when we do the difference images, we basically can derive the calibration offsets between the 2 modules. So that's shown in the top figure to the upper right, and we can clearly see there are blue regions and red regions that indicates that there are offset positive or over subtraction or under subtraction in other arrays. And we can further characterize this by noticing this fact that there are 2 patches of skies. Actually, they are observed in flipped order. So one patch of sky is observed by module B in epoch 1 or module A in epoch 2, and the other patch, the paralleling patch, is observed in module B in epoch 1, then module A in epoch 2. So we can, so if we take into account those 2 patches and add those, that systematics that are corresponding to the array, the AB difference is canceled. Then you will only left with the epoch based or time of observation based systematics. That's what the dash, the slanted black line in the bottom left plot show. We can see all the offsets actually line up on that line, indicating that there's no dependency of the systematics due to the time of the observation. Everything we see, the offsets are due to the mismatch of the calibration between the module A and B. And we can further see that the JWST calibration team has been improving this calibration with upgraded P maps. And the red line, the red point on the right side, bottom right, are the old P map, I mean the January P map. And then with the latest one, it's actually the blue and green ones. And the green one is for a sanity check, comparing the epoch 3 with epoch 2, where epoch 3 is supposed to be identical to epoch 1 because it's a 360-degree flip. Okay, and we can see there are improvements in chip 1 and 3, but chip 2 and 4, they are still at a level of around like 4 to 5%. So we have provided a recipe to kind of cure this problem, and you can check out the GitHub link there. And there's nothing there yet, but the paper will be submitted next week along with the updated everything. Thank you.
Excellent, thank you. Next.
Aha, I'm green. Good. All right. All right. Hello, everybody. My name is Aaron Shaw. I'm assistant professor at Butler University in Indianapolis, and I'm going to briefly show you my poster today. I'm trying to do something with JWST for which it wasn't designed, but it is capable of doing, and that is observing high time resolution phenomena. So fast phenomena, less than, let's say, 1 second, sub-second phenomena. On the right here, there's a little kind of schematic of various astrophysical phenomena, and the band shows the JWST, the horizontal band, shows you the sub-second regime, and the vertical band, which is kind of lost in the colors here, but sort of shows you the JWST's wavelength regime, okay? And so in the sub-second infrared regime, interesting phenomena include accretion and outflows in X-ray binaries or any accreting compact objects, even very rapid stellar occultations by trans-Neptunian objects, and of course pulsars, which all of these are sort of understudied in the infrared. Okay, and so to be able to kind of probe these these fast phenomena, we need to be able to know what the clock of JWST is capable of, how accurate it is, okay? So we've set out to kind of get a handle on how accurate JWST's clock is, and we did this by observing a check source. This is an eclipsing double white dwarf binary. It eclipses every 6.91 minutes. Its timing solution is incredibly well known from ground-based GPS-calibrated timing observations at multiple wavelengths. And this is something that doesn't change. This timing solution doesn't change over wavelength because it's an eclipsing source. So what we did is we observed this source twice over cycle 1, once in February, once in June this year. And we observed with NIRCam, we were just trying to get as many photons as possible, so we used the shortest wavelength filter. And the basic idea is if you take the light curve from JWST with the times that JWST has assigned to it and compare it to the timing solution that's very well known from the ground and basically literally just calculate the offset, that gives you a first guess of what the timing accuracy of the clock is with JWST. And so this is very, very early results. We believe we can do better, but for now, the timing offset tells us that the absolute precision of JWST's clock is somewhere around 0.2 seconds at the minute, which may not seem like we're probing down to those 0.1 second levels that we care about, but it's a lot better than the pre-launch requirements, which were around an accuracy of about 0.5 seconds per ground contact, okay? The next thing to do, that we want to do at least, is check if the clock drifts. Okay, so that's very, very important. If the clock drifts throughout an observation, and we can model that, then we can apply that correction to any science observations we do. So my poster is in physical form as well as on the iPads out there, so please don't hesitate to go and look at it during the lunch break. I'm around, so please ask me any questions. Yeah, I'll leave it there. Thank you.
Excellent, thank you.
All right, folks, thank you. So I promise it's a 5-minute thing. So I call this exploiting JWST TSO's data's full potential with FGS GuideStar data, but actually after writing this thing, I realized that this is not only interesting for TSO folks, it's actually interesting for all of you. So hopefully you will find it interesting as well. I just wanted to give a huge shout out to Dero Deal. This was a summer program student, an undergrad that was working with me during the summer. He's amazing, and most of this was led by him. He's out for grad school, so you see his application around. He's awesome, so you'll be lucky to have him. So what is this? So the JWST fine guidance sensor, is what keeps JWST on track through a loop with ACS. And it's not only interesting from an engineering perspective, it's actually a huge, massive instrument for doing science and for keeping track of your own science as if something happened during your observations. Virtually every JWST observation has an associated FGS data. And actually this comes in the form of sometimes hundreds of thousands of frames, they look like this ones. And they have very, very tight time resolutions, like 64 milliseconds. It's very, very precise in time and also in flux. It's quite amazing the precision you can get out of this. You can download this in theory and just generate like time series out of this data for your observations that is taken simultaneously with your observations. Why would you care? Should you care about this? Well, in time series observations, we have done a lot of work on figuring out what happens in time with JWST, and we have seen several kinds of events. One particular ones that whether we love or some people hate, I love them, are the tilt events. So here's an example from this beautiful paper by Lily Anderson in which we saw one of these tilt events. It was just like a little swap of the mirror, so to speak. And then what we saw, this was a transit event. So you see this beautiful JWST light curve, and there was like a break at the middle. So that's an instrumental effect. So with these JWST observations, we had the opportunity to look at the actual spectrum with a time resolution, which was fantastic, over 8 hours. And you can actually see that the full width half maximum of the spectrum changed just suddenly at that point. So that's how we knew it was like an instrumental artifact. If you have a long exposure, you're looking at your favorite galaxy or whatnot, you typically don't have this kind of time resolution at this precision. The beautiful thing is that you have the FGS data at your disposal. And that's where we come in. So you can do the exact same analysis with the guide star data. Actually, on the same observation, if you look at the guide star, if you look at the width of the PSF of the guide star information, you can actually see the exact same break at the exact same time with a beautiful resolution. So you can use this to track what's happening during your observations. Now, granted, using this fine guidance sensor data is not as easy as it seems, but we made it easy for you. And that's where we come in. So we created a package called Spelunker, and it's a pipeline to perform quick analysis on nearest FGS. It's extremely easy to install and extremely easy to use. You're in Python right now, do pip install Spelunker. You can get your library done, and then you can just read your data set doing spelunker.load. You input your program ID, and that's it. It was developed by D-Road and myself over the summer, allows to download and analyze FGS data. And if you want to do like the nice plot that I just made before, for instance, to measuring the width of the PSF, Spelunker does that as well. It's very easy. You select your program. You can get photometry for your guide star data. And in just one line of code, you can get the exact same plot that I got you with the library. So go ahead, use it. If you have questions, happy to answer them. So that's it.
I shouldn't have been worried. That was only 4 minutes. I saw those slides. Well done. Okay, I think, Marco, this is the end of the session, right? So lunch, everybody enjoy lunch. Please don't make me buy lunch for people who paid for their lunch, but there are no lunches, because that's our plan, is that I will pay for them. Buy them a lunch somewhere. We'll be back at 1:30, yeah, okay. And there's still those folks out at the tables. I actually stopped and gave feedback, so, it was fun. And there was something else I want to say. Oh yeah, and the Advise Us thing. When you're done with lunch and you're just sitting around pondering on all the great things you've heard, maybe type in your favorite enhancement into the Advise Us channel. I've already gotten great feedback on the one I typed in. All right, thanks everybody.